I don't remember for how many years now, but it's a long association with this organization for 30 plus years. And whatever you can see here, it's because of the hard work of him and Professor Ataur Rahman. They have given us such a good environment, such a best infrastructure for the research. And it's indeed a blessing to having people like him and Professor Atta with us. They are instrumental. They have developed several organizations, not only here, but also abroad in Nigeria and in Malaysia, China, and many other countries. Similarly, whenever they just touch any organization, that make them as gold. And that is actually the dedication, the commitment, and the sincerity and purpose which they have. I have been working with them as a student and then later on as a faculty member for now 25 years. My association with them is for span 25, and I always find them extremely hardworking, extremely dedicated, and that's what we learn from Professor Iqbal and Professor Atta, and they just always pushed us for hard work, and that's how you see that every day in this center you will find academic activity, and that is the legacy which we inherited from him. That this institution is always, you will always find every day, this is an institution which is breathing, which is a live institution. Every day there is something happening, something positive happening, and that is because of the ecosystem which have been provided to us, and that make us distinct. And with this, I will not take much more time, but these are something which is from the core of my heart. I wanted to share with you, and thank you, sir, for being again with us, and we are very much looking forward for your lecture.
Ladies and gentlemen, somewhere, girls and boys here. And my very dear the director of the Institute, the legacy, reflection, continuity, and we see ourselves in here, and we would really see this institution growing under his leadership. Okay, so without taking much of your time, let's indulge into a journey of a very exciting science which emerged over 100 years, science which eventually lead to your introduction to the world of nuclear, the smallest thing on the face of the earth after subatomic nuclear, and a science which make you talk to them. You can literally talk to nuclear, and you can listen to them. They sing for you, literally. They'll tell you about through their melodies where they are, from where they exist, where they live, how many of them are there, and in which environment they live in. So this so-called melody of magnetic resonance was discovered literally for hundreds of years before this technique was developed. You know, if you look into the development of science, it has never been linear. It is circular. And I tell you, this is the part of the philosophy of science. That someone discovered, someone based on that developed, someone finds weaknesses and limitation, and someone then again discovered and improve. NMR spectroscopy is a classical example of this sequential process of scientific process of discovering, rediscovering, learning, relearning, and eventually developing something which has to be developed further. While this phenomena of interaction of electromagnetic radiation with matter has been literally as long as Isaac Newton back in 1600th century. NMR is the most researched spectroscopic technique. As if 1950s, people were still trying to develop NMR spectroscopy. While Raman spectroscopy was discovered back in 1900, UV was discovered back in late 1800s, IR was somewhere in 1920s, X-ray was in 19th century, and of course 1912 when it was developed as a structural technique. NMR was developed only in the most recent. On top of it, you know, ironically, this technique was developed, we thought the whole concept was none of the science which you see in the field of spectroscopy has seen a transformation in terms of theoretical understanding. UV, when it was developed, was an electronic transmission. It remained an electronic transmission from today and would always be electronic transmission. Right? Infrared spectroscopy is talking to the bond, is more of talking to vibration and stretching of bonds, and that is a kind of an energy which infrared provided. It could remain be like this forever. So X-ray crystallography was scattering of electrons, X-rays with electrons, and that scattering would remain the same forever. So somehow would continue to work on the technique that was developed 100 years ago, and nobody can change it. Same goes to all other fields. NMR has really seen a transformation. Both in terms of instrumentation and in terms of theory. It was developed fundamentally as an absorption spectroscopy, as if for UV and IR. Essentially the same with the difference of only magnetic field. But it has really gone through a very, very different dimension. When somebody said, stop recording absorption. Let's discuss about electricity. An entirely different phenomena in the spectroscopic world. The entire theory was changed. And that theory has transformed NMR spectroscopy into a different field. That makes NMR essentially a technique which evolves every 10 years. That brings new theory. Somebody said, why do we need to excite nuclear spins? Why don't we just, why do we need to excite them one after the other? Why don't we just excite them all together? Right? Giving a pulse of radio frequency. But I'm going to tell you that this is a technique which can be as simple as easy if you try to understand superficially, and it can also be a bit more tricky and difficult and challenging. And therefore, it goes, which I really found very difficult to accommodate in my schedule. When I'm visiting 30 countries by the end of this year, I still think it's very, very important that we should start talking about field, which has so much fundamentally changed the whole world of science. Also, so much so, you see, chemistry phenomena such as arithmeticity. I mean, arithmeticity, if someone has really thought about it, even to mundane thought of a snack with detail inside the mouth, right? How would you prove it? NMR was the only technique which has experimentally proven arithmeticity. Electron donating effect, electron withdrawing effect, partial positive charge, partial negative charge, the conjugation of double bonds, all of that in a piece paint you can discover by UV IR. But as a whole, as a molecular structure, NMR was the only technique which proves these concepts. So conceptually, it has proven a lot of age-old chemical theory phenomena. None before any technique has proven that. So that has fundamentally changed the conceptual framework of chemistry as well. And then you see the numerous examples of it. I mean, of course, visible spectroscopy, to some extent, other spectroscopy techniques are used in medical diagnostics also, such as X-ray. But MRI has changed the entire diagnostic. I mean, it's far superior than CT scan or ultrasound, CAT scan, whatever. So you see, this is NMR, which now is the most powerful tool of medical diagnosis, magnetic resonance imaging. And so much further. Application, literally everything. This is the most versatile technique which is used in food science, which is used in solid state material sciences, which is used in drug discovery, development, which is used in forensic sciences, which is agriculture, adulteration, hydrocode, and others. So numerous versatile examples and use of just. It is therefore. You think of it, if you buy a Mercedes, I don't really know the prices of much expensive cars. You may know about it. I know a deal with a rich person. You may have a Porsche or something like that. But if you, isn't it shared? But his way he drives his BMW, goes to Federal. But think of it, you have a Mercedes. We have Mercedes, 13 Mercedes in a range. And if you use Mercedes for your grocery, like big bag of atta and aloo and that. If you don't understand what else Mercedes can do, apart from transporting your grocery, then exactly what you're doing with these buses. The overall investment of the teams per capita in the institute is literally billions of rupees, millions of dollars. It's so much important for you to understand the nuts and bolts, the power of advanced math, what you can do with it. It's not per se is proton NMR spectrum which you require. Or if you're brave enough, you go for C13 NMR. The fact is, these machines, even the oldest one, which was purchased in 1981 and is still got, they do lots of much bigger samples and help you in looking into the invisible world. looking into the structures which you would never be able to see. You know, for X-ray, you have a crystalline substance. Only 5 to 6% of the world come out, but they have the tendency to be crystalline. Tritium is still a very nascent state. Costing about 10 million USD, we know that is not money. So NMR will be a very important technique for you to see that there's so much of techniques available. Therefore, it is important that you understand the basic fundamental to that. Okay, so this is one book in 2 versions, but in fact from the institute, our teacher, Professor Dr. Karan has written another books. One is called Two-Dimensional NMR Spectroscopy, the right approach, and the other was Fundamental of NMR Spectroscopy. We have been invited, because this was a blockbuster, we've been invited to write the 3rd version of it. But for that, we need to have time. That is, what's the name? So, and okay, so you don't really need to worry at all about writing anything. These lectures will be in public domain. You will get them. They will be placed on institutional website. So you will be able to see a lot of them. And they are, you see, simulations, animations can help you to understand. There are a lot of other concepts which writers often avoid when they write books, because they kind of bewilder and confuse the readers. And I promise that I'll do the same. Because of a simple reason that NMR is not straightforward. Second is, it has to be inherently and by design repetitive. Because it is kind of a very slippery thing which is in your hand, and you lose it. So you need to hold it again and again. Okay. This is the reason why you find NMR spectroscopy is called highly repetitive. You would find that there would be sometimes necessarily or unnecessarily repeating some of the concepts. So of course, the intentions are very, very important, that I really want to. Then there is a whole series of books which we have edited, not written. It's called Applications of NMR in different fields. And each book is dedicated to a particular field. The use of NMR spectroscopy in food science, use of spectroscopy in geological formations, minerals, the use of NMR spectroscopy in medical diagnosis. So there is a whole series of books which we have edited. That is also a useful addition for you if you wish to. If you wish to dive into some of these more detailed accounts of the application. You haven't really seen things in its entirety. If I tell you that we were in the process of buying an MRI for breasts, and at some stage you'll buy that. MRI for reps, how exciting it would be that you pick a two small rats and then you put it in MRI machine, and then you get the entire MRI for complete rat. Right? Isn't it exciting? And then all kind of angles, including rodents and humans and all that. But this is a machine which I'm sure that you have seen it for because of something. maybe some of your relatives had need that something. You know, difference between the one which we have in our institute and in many places, and the one which every medical facility would have it within the large one, is just horizontal and vertical. This is like this. Okay. Vertical, and this is like this, horizontal. Nothing else. No change. It is NMR for medical diagnosis. This is NMR for chemical and biochemical. Now, think of it. Why the name of the technique was changed? That's an interesting history. It used to call NMR for medical diagnosis. The name was so scary. Nuclear magnetic resonance spectroscopy for medical diagnosis. Nobody wants to go close to nuclear, right? Too scary, even India. Okay, so nuclear was so scary for them that the name was changed because nobody was coming for diagnosis, just a perception that it has anything to do with nuclear science or nuclear medicine. So, but this is actually the same. Here you place your sample here which goes into. Here you place a person like this. Here you record proton NMR spectrum of your chemical hydrogen. Proton is hydrogen. For protein, right? There are three isotopes of hydrogen. Here you record proton NMR spectrum of water present in the body. 70% of the body is water. Exactly. Essentially, the entire theory, MRI, and NMR spectroscopy. You see, this is the yes. The same magnetic field inside. You see some videos. There is some photo moving around. Okay, so think of it. This NMR tube, which contains sample, moves very fast, very fast. It is rotated inside. In order to, very simple, and the everything which I am actually speaking right now is going to be repeated and again and again and again. Okay, so this spin is called rotation of the tube because you want that magnetic field which is applied with uniform. If you do exactly the same person with the person, if you rotate a person with the same speed, what will happen? You don't really want that thing to happen, right? The brain would be like a yogurt. And you don't want to record the NMR of yogurt, the brain. But what he's actually talking about is three components of the magnet. Okay. Outside there is a magnet, inside there is a gradient coil mode. Because gradient coil provides a micro Tesla field for focusing the cell region. And absolutely inside, and that is the voice. The noise comes from the gradient coil. And inside there is the radio frequency. Okay, so tap, 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 tap. All these sounds coming from the gradient coil. So, having said that, the one which we have in our institute is 800 megahertz, about 18.5 Tesla. It's a very powerful machine, costs you about 250. You buy it now. So, and now the alert development, yes, sir.
NMR में ट्यूब को फीड करने का मकसद क्या है? हम उसे स्केल पे क्यों नहीं करते?
Okay, so there is one option that I start. Let me respond to you. There is a magnetic field, but we haven't really defined magnetic. We haven't really learned anything about NMR, but let me respond to your question. When you have a sample, and you have a magnetic field, even the best technology in the magnetic field, there will be some inefficiency, some inaccuracy, and some difference in magnetic field. If you rotate the center, you average it out. Okay, so that is the objective of it. Anyway, so this is what I intend to do. There are going to be some 10 lectures. You would not really see me very often, but I would appear on the stage from many levels. There are going to be two lab sessions where our colleagues will take you to NMR lab, and then going to be 4 interpretation skill development modules. And these girls on this site, they are experts in NMR spectroscopy. They will send abroad. They know NMR better than me, but they put me on the stage because they want to know. Okay, focus on developing fundamental concepts. That is the most important. See, concepts are important. If you know things from the conceptual level, that you would be able to apply them much more effectively in whatever the field you wish to, organic, bioorganic, and others. And as I said, that you would be visiting our NMR laboratories, as I will expose in my absence, and Dr. Mehra Zafar and Dr. Mehra will be the resource persons for interpretation. You can WhatsApp me any question. I don't mind receiving salam every day, but it's difficult. 600 salam every day. It's going to be difficult for me to respond because I do really respond to every salam. So, okay. And then, of course, email. Okay, email. And these are the learning objectives. This is what we intend to achieve in terms of outcomes. See, we would like you and us, because this is a mutual learning, to understand the fundamentals of nuclear magnetic resonance spectroscopy. And to review the difference between the classical and modern NMR spectroscopy. As I said, NMR has really gone a transformation from somewhere as an absorption spectroscopy to an emission spectroscopy, and now something else which I don't really know the name. Because you don't really record radio frequency anymore. You record electrical impedance, which is FID, and I don't have a name for it. Even in the basic definition spectroscopy, there is no name for this kind of a phenomenon which exists in it. You know, the basic definition of spectroscopy is absorption, emission, scattering, isn't it? But nothing like this is now there. NMR spectroscopy, so the difference between classical and modern. Of course, to discuss the development of solving sensitivity. NMR spectroscopy is the most insensitive technique in the world. Insensitive not as a human behavior, right? Insensitive in terms of the quantity of samples which you can detect. It always needs something in your hand which you can see, right? In mass spectrometry, you can do it in literally now femtograms. UV is just so absolutely sensitive that even few molecules will be sensitive. IR is also very good, but when it comes to NMR spectroscopy, you need sample which you need to isolate. You need to have, if not milligrams, at least a few nanograms. So sensitivity is a major problem. Most of the development in NMR spectroscopy has been driven by sensitivity problems. Most of them. I would say 90% of the development in NMR spectroscopy has been driven by a strong desire to make this technique sensitive one. So you can analyze minor samples. And to understand the nuts and bolts, means the hardware. What kind of hardware you need in order to record NMR spectrum. NMR is a very scary looking equipment. Look like a rocket launcher, literally, which goes up and in the heaven. But very unlike of UV, IR, which are gentler, smaller, flat machines with good screens on the desktop, NMR is scary. Really, sometimes you need to climb on the stairs to put your sample in because the large pack requires. Sometimes you need to dig a hole in your floor in order to place it. Because magnetically it's so sensitive. Magnet is so effective. That even the small disturbances can change the magnetic field. So we'll discuss about, and in that case, we'll take you to the lab. We'll also show you the most important part of NMR, which is probe, right? Carrier probe. And then, of course, practice the application of various NMR techniques and solving structures. That mathematics would actually take care of it. And to discuss the future prospects of this fast developing technique. These are some of the learning objectives. Outcome, in-depth understanding of NMR phenomena in historical context. How this technique has been developed. Why it took about 100 years to develop NMR while other techniques were developed literally in days and months, right? And then capacity to utilize a wide range of NMR experiments and techniques in them in your own research. That is the most important part. The course content would be brief introduction of spectroscopy technique. It's important to define the context. The definition of spectroscopy technique is also changed. You know this. And that we will discuss. And where you place NMR in this application. So the fundamental concept, the techniques and approaches to enhance sensitivity, introduction of 1D NMR to begin with, and then a very important technique, polarization transfer, for solving problem, which has actually led to the award of Nobel Prize to Professor Richard Dance, and inverse NMR experiment, introduction of 2D NMR spectroscopy, polarization transfer, and its inverse, and full space government and application. Okay, so I will begin by James Belvin, a very famous biophysicist in Oxford, Dyson Banyan Laboratory. Belvin effect, Belvin reactions, are known in organic chemistry. And he said what? He said it is probably true that NMR spectroscopy has had the greatest impact on chemical research since the development of the accurate balance. You find it interesting. You think accurate balance was a very important development in chemistry? Yeah. Was it very important? I mean, the whole stoichiometric calculation, whole polar calculation, everything based on accurate balance. And that enables you to develop an entirely new field which is called analytical field. And that's interestingly both of these techniques, weighing and mass and NMR, weighing and NMR are based on the same nuclear profile. You know that wave of substance is primarily a nuclear profile. If you go up, you become weightless, right? So it depends on the place you are in. And this is the definition of NMR spectroscopy. Classical definition and new definition. Study of molecular structures, dynamics through the absorption, any technique with absorption, emission, scattering of light, electromagnetic radiation is the classical definition. The definition has been expanded now. Now spectroscopy, because at some point of time, until 2012, mass spectrometry wasn't really called as a spectroscopic technique because it doesn't really use electromagnetic. You know this, right? Mass spectrometry has no involvement of electromagnetic radiations. These are fast atoms or fast electrons, right? Electron work. And neutron diffraction, a very important technique in which neutrons are bombarded. So all these techniques were not a spectroscopic technique because this definition was just so absolutely conservative that it wasn't able to embrace a new development. As a result, a definition has been modified and it says as well as the particle, which means that particles, when collide to your material, is also become a spectroscope. And that includes neutron diffraction, that includes mass spectrometry and others. So this is the definition of spectroscopy. Now, I'm sure that you know absorption spectroscopy. A lot of absorption. UV and absorption spectroscopy. Visible is a spectroscopy. Raman is a absorption spectroscopy. Emission also, you know, IR has been transferred into emission spectroscopy. Sketching, you know, already X-ray. But NMR doesn't really fit anywhere. NMR is neither absorption. The radio frequency is absorbed. You don't measure that. Okay. Or emission, radio frequency is never come out. In NMR spectroscopy, radio frequency goes in, never come out. In UV goes in, UV come out. IR, infrared goes into the system, infrared come out. X-ray goes in, X-ray is reflected. In NMR spectroscopy, radio frequency goes in. I don't know where it goes. It converts into electrical signal for impedance. So this definition is still insufficient to include NMR on a strict sense, right? But this is what it is. It is part of a scientific cyclical process. I used to teach philosophy of science also. And at some stage, if I find time, I will. You see, science, how science evolves. You develop a theory. Somebody else experiment, and that theory convert into a phenomena, a dogmatic principle. You say, this happened like this. Okay. The gene products convert into RNA, RNA convert into DNA, whichever. That's called central dog. Right? Then some people start experimenting and they find exceptions. They say, oh, you know, there is something really which doesn't fit in this theory. And that exceptions accumulate to a level that the entire building of that theory collapses. And people then bring a new theory. It's called scientific philosophy. It's a philosophy of science. Exactly same thing would eventually happen, and then somewhere, somehow, somebody would actually devise itself. And this is electromagnetic radiation. It's not to be completely linear, it doesn't show anything like that. For instance, cosmic rays are the most strong known electromagnetic radiation. When I say known, because there's so much unknown. God knows who discovers something which is stronger than cosmic, right? Then gamma rays, and then X-rays, and then soft X-rays, then UV, visible, infrared, microwave, radio frequency. On one hand, you have very strong electromagnetic radiation. Why they are strong? They all move with the speed of light. No change. They all are light, you know. Their speed is exactly the same as Einstein's theory. The speed of light is exactly the same. The difference between them is energy. Because they have different wavelengths, therefore different frequency. When there's a different frequency, there is a different energy, right? So the difference between them is only the frequency and thus in energy. So these are extremely high level frequencies and these are low level. Radio waves are so common that as if I speak to you, all of you are immersed, sorry, not immersed, immersed into radio frequency. All around you is a radio frequency. I have radio frequency here, my pocket, right? You all have radio, you are immersed in radio. And it's so absolutely safe to some extent, we don't know. And each one of them, except gamma rays, is used for some useful purposes. The most important use in this case, in the field of chemical sciences, all of these techniques were developed by physicists, remember? Based on their own curiosity. Chemists were never involved in the development of the machine. They were only the users of it. So each one of that technique, from X-rays to near X-ray small scattering, UV of different kinds, infrared, visible spectroscopy, which is you also call colorimetry, infrared, IR, microwave, and then radio wave, which is NMR. They all are, essentially all of them, are used in the spectroscopic technique. All of them, without exception. So, and you also know, the classical theory of okay, classical theory. Sorry. So the classical theory of electromagnetic radiation is primarily two oscillating fields. Yes, you know, and this is just a fundamental basic physics perpendicular to each other, completely synchronized, maxima and minima are different. Section. I'm really sorry. My apologies. Can you hear me now? Okay. And you can drop your question, if any, on each chat box, because I don't really think that I will be able to respond to them right now. So this is the electrical field, and this is the magnetic field, sinusoidal. This was well before the quantum theory or particle theory of electromagnetic radiation was developed, but that is also such not very difficult. is that the photon with the same frequency and energy, it goes through the space. So, and that is the NMR, which we will discuss. So here we go. This is what we intend to use, significance. So it was developed in late 1800s. I was in 1925. X-ray was somewhere in 1890 and 1900. UV was well before. And then here's people who wonder. Think of it. Everything is absorbed. All these radiations are absorbed. You get absorption spectrum and some information there is. Radio frequency, you give it to the sample, nothing comes out. Was it a holy grail of science? The science was totally puzzled that why radio frequency, when you shine UV light on sample and you have a detector on the other end, you record absorption, emission, whatever. When you shine IR, infrared, you get some response on the other end also. When you shine radio frequency, there's nothing about it. And that keep people puzzled for literally 100 years or so. There was only Peter Zeeman, who was the first one in 1890, who speculated that the radio frequency and has something to do with the nuclear spin, and that can only be recorded by doing something different, which is not there. It was back in 1946, 45. Okay, but before that, 1939, Isaac Rabi, who was in Columbia first and then was in Bernal, he was the first one in 1939 who said nuclear spin under vacuum and magnetic field can absorb radiation. He was the first one. And he has absolutely no idea that this can be used for structural sedation or chemistry. He was a physicist of excellence. He was a physicist who came from Poland, who was a Jewish scientist, migrated to US, and then he was part of a Manhattan Project. How many of you know Manhattan Project? How many of you have seen Oppenheimer movie, Netflix? This one. Again. How many of you know that there were 14 witnesses in support of Oppenheimer? 28 of them were betrayed, as it happened in many countries. This was a developing country at that time also. Anyway, so Isaac Rabi was the first one who discovered nuclear space. And that led to theoretical foundation of two completely independent groups. Independent group. Robert Purcell, okay, in Stanford, and Flex Bloch in Harvard. Two of them completely independently working, knew nothing about each other, was further investigated, work was conducted when they were awarded with the Nobel Prize in 1951. One was working on solid samples directly. The other group was working on liquid samples, water. Same of them, both of these groups published two papers in the same issue of the Annals of Physics in January 1936. Same issue. Such coincidence in science is just absolutely mind-blowing. Two groups independently working on the same thing, published paper in the same journal, in the same issue. Okay, and what is that? Let's go in person. They got Nobel Prize in 1950. And they were completely unaware. What they have done, they converted the theory of Isaac Rabi into practical and recorded the nuclear spin, emission and absorption of the radiation in its radio frequency for two samples and recorded NMR spectrum. Okay, so I think I'll let my colleagues discuss this. But this is what the classical spectrometers even today are exactly the same. You know, if you go to any laboratory of the world where you have UV, IR, Raman, even X-ray and others, this is what happens. A source of electromagnetic radiation, you agree? Source of electromagnetic radiation, your sample, right? Like your electromagnetic radiation is absorbed, emitted, or scattered. You analyze and detect, and you record. Nothing fancy. Electromagnetic radiation source, appropriate frequency, then monochromator, you know that from the radio frequency spectrum, you can carefully select only one wavelength or a range of a wavelength by using prisms, right? You have done it. So they call monochromators. A sample holder where you place your sample. Now, it could be KBR disk, it could be liquid sample by UV, family dissolved in fluid form, or others, and then frequency analyzer of absorption, emission, and scattering. Then a detector which detects the intensity of frequency. And then recorder. So now it's computer. 100 years ago, the equipment was same as today, and better rate. Absolutely same. The difference is, in order to get more money from you, they put it in one box. Okay, they put it a nice color. They have a small computer screen on it, touch button, right? A Wi-Fi you can get transfer the sample, maybe a database connected to it also. Inside it is just same. Everything is essentially the same. No change. Even the most expensive equipment which Dr. Summer has is same, right? X-ray is generated. She has a crystal here. She has a detector, and then she take that spots which are recorded in detectors, use mathematics, convert that into alpha density. She gets the X-ray structure. Right? Everything is actually the same. Problem was that it was not working for radio frequency. You have a radio frequency, you have a sample, you have everything, nothing was coming here. That was the Holy Grail. You know Holy Grail? Okay, I want you to read about it. Holy Grail in Christianity was a piece of cloth which was in which Jesus Christ was wrapped. And that exists in Rome, and people are trying to understand whether this really belonged to Prophet Isa. Okay, so there are a lot of speculation about it, and since hundreds of years, everybody is debating about it's called Holy Grail. Okay, so this is the Holy Grail of science. And it was only accidentally. See, lots of development in the world of science has been the results of conflicts. Second World War was the most important event in the history of the world for development of science. Science always developed in crisis. The most important science developed in this era was during COVID-19. You know this, right? Crisis make people think. Constraint make people innovative, right? And that is the reason that many of the development, whether radar or missile or NMR, was a result of Second World War. Or splitting of atom. Splitting of atom, you know, which now is the most important, cleanest, finest source of energy, was done during Second World War. And this is exactly what happened. What they were doing was, the World War was over, and they didn't know what to do with those machines, which they were using for the development of radar and others. And this tremendous resource which was provided to them during the war then turned into something extremely important. They said, okay, why don't we just look into a basic fundamental phenomena that when you place your samples under the magnetic field, how they behave. It has no intention of developing of NMR. It was later was recognized in turbine theory. So what they've done was that for everything, for UV, IR, etc., 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 they put a permanent magnet here along the sample. Complete theoretical, accidental, beautiful, serendipitous discovery. And all of a sudden, they see the signal of fire or radio wave. All of a sudden, they have seen the absorption of radio wave. Phenomenal, right? And that was a discovery by Flex. Looking herself that they were, and then later, they linked it with the Isaac Gabor theory, which said that nuclear spins resonate in low energy and high energy and can absorb radio frequency. What do you think what has happened? What magic has happened that this small little magnet around your sample holder has changed the entire field of spectroscopy? I'll ask you a question. Why electromagnetic radiations are absorbed? No, electromagnetic radiation are absorbed. They are absorbed because there are two energy levels. And something has to go from low energy to high energy, right? Radio frequency wasn't really absorbed because there was no energy state. As soon as you place your sample in magnetic field, magic happens. Two energy state created, radio frequency was absorbed, spectrum was acquired. Okay? This was a fundamental basic discovery which led to the Nobel Prize to these two finest individuals in the world of science. So let me, I have just added questions into that. And you don't really need to respond. But these are the questions which will enable you to understand a bit better molecular spectroscopy and atomic spectroscopy. Okay. Some of them would also be part of your assessment. It's not a guest paper, but it will be rephrased. Atomic spectroscopy, you know spectroscopy, but do we really know what means atomic spectroscopy and molecular spectroscopy? Then I leave it to you. Don't need to respond to it. And now, nuclear magnetic resonance spectroscopy. You place a sample in magnetic field, magic happens, and a new field emerges called nuclear magnetic resonance spectroscopy. There is no other field which is so descriptive. The name suggests everything. Name suggests everything about it. Nuclei of elements, right? Magnetic, because you need to place them in magnetic field, and they are magnetic by themselves. And when you do that, when you place your sample, all of your samples are atoms. All atoms have nuclei. All nuclei are magnetic because they have charge. And when you place a small magnet into a large magnet, something happens. And that something is resonance. Okay? So the name itself is 50% of the theory. If you understand the name, you don't need to come in next class. Okay. So nuclear magnetic resonance spectroscopy. Study of nuclear spins. Everything has spins. Atoms have spins. Ions have spins. Electrons have spins. Neutrons have spins. Collectively, all of them, subatomic particles have spins. And same, protons have spins as well. And nuclear as a whole, and everything, nuclear is the most condensed part of the atom. Think of Sahara Desert in Africa, next door, right? And one sand particle is a comparison between the atom as a whole and the nucleus inside. It's so condensed, it's so small. People would never be able to see nuclei. And when I say never be able to see nucleus, I'm wrong because I don't really know what will happen in the future. I'm just guessing. Okay, you can only predict by using various things. This particle accelerator in is actually accelerating this nuclei and then bombarding them with different types of particles. And energy is measured, and as a result of it, we know what it is. And then you need to place them in the magnetic field. Think of it. The magnet which was used in 1945 was a permanent magnet. Permanent magnet. Permanent magnet for children play. Copper needles, iron needles, the coins, etc. Right? All magnetic metals. Permanent magnet. There was no development of electromagnet before 1955. Because in 1955, when electromagnet were developed, when electromagnet were developed, permanent magnet were discarded. NMR was built with electromagnet. We have one in our museum. You can go and see by yourself. Okay, we bought that. We were among the first users of NMR in the developing world. Right? We started using NMR back in 1976 or something. And the NMR machine which we bought in 1981 had a number of 100. It means only 99 machines were sold to the world before us. So we were forerunner in the use of NMR spectroscopy, electromagnet. And then it wasn't really so sufficient for sensitivity. Because then there is a relationship, direct relationship between magnetic power and sensitivity. So superconducting magnets were developed in 1970. And the one which we have is the superconductor. So in the next 5 minutes, I'll tell you that the superconducting magnet, starting from very humble 1.5 Tesla machine, the one which we have right now is 18 Tesla machine. It's a huge magnet. Why is it called superconducting? Because it's a magnet of excellence. It has a nearly close to zero resistance and nearly 100% conductor. This is the reason why it's called superconductor. And the one which are now available, you see such a beautiful NMR spectrum. You agree with this? You like this? Physicists absolutely didn't like it at all. You know, physicists has nothing to do with chemistry. They are a different species, living in a different planet. Okay, to them, it was totally confusing, incomprehensible that they put alcohol or water or paraffin, and instead of getting one peak, they get 3 peaks. And they said, this technique has some problem. And they call it chemical shift. They call it that the compound has some problem in it. Well, the machine is okay. Has some problem in it, and that is the chemical shift. You know, these chemicals are crazy by chemists. So they are moving here and there, and the result of it, instead of giving one peak which they were expecting, from proton, for them, proton is proton, hydrogen is hydrogen. Right? Carbon is carbon. But only chemists were the one who knew that all protons are not same. All carbons are not same also. So chemists were very happy to see this spectrum. And they were happy that this is ethanol. They were happy in 3 accounts. Number one, they always thought that ethanol has 3 peaks. You know, well before the development of NMR, a lot of organic chemistry was done. They knew that ethanol has 3 different types of hydrogens. Electronically, not that they are not different elements, they are the same elements, but they have different electronic environment. They were happy because first time in the history of the science, they were able to see what they used to think. Okay? They were also very happy that they always knew that methyl has 3 protons, which essentially are same. CH2 has 2 protons, and OH has 1 proton. And this is exactly what it is showing. A large integration for 3 protons, a small integration for CH2, and a smallest integration for. And they were absolutely brilliant. While physicists were in mourning, sadness, chemists were jumping with, right? And in between, the technologists came. They said, okay, let's have a mutual coexistence. Let's live together. Let's have harmony in this world. We'll help you to build better machines, which chemists will buy. Okay? when they will buy, you would have salaries. Right? So this is how the things will develop. But now, I want to look like this. One thing added. Now you can see the splitting. Right? And I want to show you, this is called high resolution proton NMR spectrum. High resolution. Such a joke, right? But science is always a joke. So, in terms of understanding, and is a fun, And then they see something else happen also. They see that not only the types and number of protons, their returning environment, but also their neighbors. They find what NMR does. I'd like to end this here, inshallah, and thank you very much. Thank you.
Sir, I have an announcement while you are here. So tomorrow we'll have lecture at 10:30. Rest of the lecture will be at 10:30. I want to ask, have you seen the book? When?
No.
Just now, right? Do you want to have it? Who wants to have it? Raise your hand.
No, good point. It's so difficult.
Okay. So whoever wants to have it, you have to earn it, right? So Sir said we'll have assessment in the end. So I requested yesterday to Sir that we want to give one of the book signed by Sir and authors to the student who will score highest.
And you'll get it from the director.
Yeah. Thank you.
Okay, thank you very much.
Yeah.